4 blocks here. Includes semiconductors, transistor, amplifier, oscillators and multivibrators, power supply and regulation. Okay, so let me start today semiconductors. So in this semiconductors, we had 3 topics. One is that semiconductor junction diode, and second unit is the transistor configurations. So third one is the special semiconductor. Yeah. So before going to discuss about the semiconductor devices, so let me know you that here each and every atom here, the entire universe, which is made up of matter. Here matter consists of here atoms. Okay, so here each and every substance which is made up of atoms, where the atoms which are going to be arranged in a systematic manner. So that's why here let me say that if you observe each and every atom, the atom consists of a nucleus. Around the nucleus, the electrons which are going to be revolve in different orbits. You know that. So the thing is that here, suppose if you consider a sodium atom, let me say here. What is the electronic configuration of the sodium atom? 1s2, 2s2, 2p6, 3s1. We are to be considering only one atom. That is a sodium. The electronic atomic number is here 11. According to the sodium atom atomic number 11, we are to be writing here the electronic configuration is 1s2, 2s2, 2p6, 3s1. Okay. So here, according to the shell here, K, L, M, N, like that here, if n equals to 1, the shell is K, n equals to 2, shell is L, M, N, like that here. The maximum number of electron which can be occupied in a shell is, the formula is 2n square. Suppose if you substitute first n equals to 1, small n equals to 1, by substituting in place of 2n square, 2 into 1 square is nothing but a 2 here. That means in first orbit, the maximum possible electrons which can be accumulating in that orbit is nothing but a here 2 only. Okay. And if you, that is 1s2, that's why you are going to be writing here 1s2. Later on 2s2, 2p6, that means 2s2 is 2 suborbitals are there. Okay, so 2s2 2 electrons and 2p6 is 6 electrons. 2 plus 6 is 8 electrons. It is to be accumulating in the second orbit. That means how it is possible 2n square. If n equals to 2, 2 into 2 was 2 square. That means 2 square is 4. 4 into 2 is 8. 8 electrons which are going to be accumulating here. Similarly, n equals to 3, 2 into 3 square. That means 3 square is 9. 9 into 2 is 18 here. 18. How? 3s2, 3p6, 3d10. 3s2, 3p6, 3d10 means 10 plus 6 plus 2, 18 electrons. So according to the electronic configuration of the here, what do you say? The electronic configuration of the here sodium atom here 1s2, here 2s2, 2p6, 3s2, 3s1, but it can accumulate one more electron, but the orbit suborbit is here, subshell is half filled here, and remaining 3p is which is 3 0, and 3d is also 0 here because of no more electrons which can be accumulate to accumulate in that particular suborbitals here. Like that, only one electron is there, that is empty here, that is half filled here. That electron you can call it as a outermost electron. You can call it as a valence electron. Okay, so for one atom, but somewhere the substance is to be considered. Let me say that 500 atoms are there. For 500 atoms, or 500 sodium atoms, 500 there. So like that, according to the band theory of the solids here, how these valence electrons, which are to be here forming a band here, and if we elaborately, we are going to be observing that band here. Each and every outermost electron which is going to be forming like a covalent bond between them. Okay, and those are to be forming a band. That band you can call it as a valence band here. Okay, so these are nothing but a here which consists of a outermost electrons. So the bond between them which is a covalent bond. So here, let me say you here the covalent valence band, which is always, what are the properties of the valence band here? Valence band which is always completely filled or partially filled, and the bond between the valence electron is a covalent bond, and here uh, this band is above the band there is another band. That band is nothing but a here what do you say here, conduction band. So here in valence band the electron cannot move freely. Why? Because of there is a covalent bond between the valence electrons, so electron cannot move freely. So if suppose if you say that here the electron which is going to be moving freely means it is going to be carrying out the charge here, one place to another. Charge is movable, charge is carried out from one to another place. You have to say that the material which is going to be constituting the current I. So I equals to dq by dt, or else you have to say that I equals to q by t. Okay. So charge to charge per time, which is nothing but a current I equals to q by t. What is the here? If it is going to be carried out by the electron, if it is to be move freely, so that is possible in the case of conduction band only. So that above the valence band, the band is nothing but a conduction band here. So here what do you observe from that? You are going to be observing that here that is here what do you say? The electrons here completely filled in the valence band, whereas or else partially filled in the valence band. And in conduction band, the electrons here which are partially filled or else empty, but here only the electron can move freely. Okay, so our aim is that here you have to break down the covalent bond between the valence electron. The electron has to reach out from the valence band into the conduction band. Then only the electron is going to be moving freely, so that it is going to be carried out by the charge. So the material it is going to be constitute the current here. Okay. So but here between the valence band to the conduction band, there is a gap. That gap which is nothing but a here forbidden energy gap. According to the band theory of the solids here, the materials which is to be characterized in three categories. You can able to observe that here. So the diagram which is going to be indicating that the first one is here insulators, and second one is the semiconductors. Third figure C which is to be indicating a conductors here. Let me talk about the here insulating materials. So the gap between the valence band to the conduction band is very wide here. Okay, you can see out here how much of the gap which is to be takes place between the EG value is also given out here. So valence band to the bottom is valence band, top one is the conduction band. Between the gap is forbidden energy gap. The thing is that here whenever you are going to be how the electron has to reach out from the valence band into the conduction band across the forbidden energy gap, how it is possible. But the valence band which consists of the here a covalent bond between the electrons here, okay, outermost electrons which are available in the which are to be forming like a band here. So that means here to break down the covalent bond, and the electron has to reach out from the valence band into the conduction band across the forbidden energy gap. So you are going to be increasing, or you are going to be giving such energy to that to break down the covalent bond by increasing the temperature here. Okay, whenever you are to be giving such energy to break down the covalent bond between the electrons and the valence band, the electron which is free now, that the electron is a free electron which is to be jumping from the valence band into the conduction band across the forbidden energy gap. This is the process. If the electron is to be enter into the conduction band, the current is to be constituted by this material here. So the thing is that here the electron cannot be reachable from the valence band into the conduction band. Why? Because of here the gap between the valence band to the conduction band is very wide. That's why here the electron is not reachable from the VB to the valence band to the conduction band. All the electrons which are fell down into the gap. That's why these materials are not going to conduct any current at all. Okay. So the best example for this materials is here wood, rubber, etc. Like that. Here, whenever where we are going to be using this insulating material means here, whenever you are to be joining any two wires here, there only we are to be using here insulating tape. That means this material is not to be conduct any current at all here. Okay, now. So that is the case. Okay. So here these are nothing but here insulating materials. Okay. So here one thing you have to know that if it is not going to be conduct any current at all, you have to assume that the resistance of this materials is very high. Okay. The resistance is very high in the case of here insulating materials. Okay, Nadi? Next one. What about the here conductors here? Conductors is that here when where the valence band, conduction band, and forbidden energy gap all are overlapping here. Do you observe that in the third figure, right hand side, which I am going to be sharing here the screen? You can easily observe that there is no gap. Okay, every band, that means valence band, conduction band, forbidden energy gap, all are overlapped here. That's what here. Whenever you are going to be giving such energy to that, easily the current conduction should takes place. That means here the electron easily jumping from the valence band to the conduction band across the forbidden energy gap. Okay. So the best example for this materials is here copper, aluminum, like that. Where we are to be using here these materials in household, everywhere we are to be using here copper wire, aluminum wire, like that here. Whenever you switch it on, the fan is to be rotating. Whenever you to be switch it on, the light is to be glowing here, like that. Okay. But when the temperature is to be rises here, in the case of conductors, so there only you have to imagine that uh, here up to certain temperature the conductivity should takes place by these insulating conducting materials. When the temperature rises means here the flow of electron which is increases. If the flow of electron increases means it is to be colliding with each other and also colliding with the walls of the material. Friction developed. That's why here temperature is rises. Suppose the material is to be hold up only 500 electrons. If more than 500 electrons which are coming across this wire or the material, that wire or the material is not to be hold up these many of the electrons, so that the electrons which are to be leaking out from the material. That's why you have to say that the short circuit is to be takes place. That means the leakage should takes place. Electrons which are to be coming out from the material. Okay, so this is the problem in the case of increases the temperature. To overcome this problem here, new materials is to be found out. That material you can call it as a semiconductors. So here between the middle portion, that means here the forbidden energy gap is very small. Okay, so between the valence band to the conduction. So at room temperature, these semiconductor materials are behave like a conductors. By increasing the temperature, uh, the materials which can behave like a good conductors. Good, okay, normal to the good. Normal to the good means here there is a more number of electrons which are available in the case of uh, temperature rises in semiconducting materials. Okay, so next up, pure or intrinsic semiconductor. Next one is the pure or intrinsic. What is a pure? The best example for the semiconductor materials is silicon and germanium. So what is a pure type of semiconductor materials? Pure type of semiconductor material means there is no here impurities which are available in the case of a pure type of semiconductor. So, but the thing is that here there is a equal number of electrons or also equal number of holes which are to be present. So where the hole is to be created. So whenever the electron is there in the conduction band, valence band, so that if when you have to be broken down by increasing the temperature, so that the electron is going to be jumping from the valence band and it is to be jump into the conduction band across the forbidden energy gap. So that where the that place is to be created, that means it is to be losing the negative charge, then it is to be becoming a positive hole. Getting my point? That means a positive hole is to be created. Again, the positive hole is to be occupied by the besides the negative electron. Okay, the recombination process is to be taken. That you can read out in the upper classes. But the thing is that here, in pure type of semiconducting materials, if 50 electrons are there, free electrons are there, only 50 number of holes are to be created. But our aim is that if you want to increase the conductivity of the material, then it is to be needed more number of free electrons. If more number of free electrons are available, more conductivity. Equal means less conductivity. Okay. So to overcome this, scientists found another materials. That means here, if you dope a impurity to the pure type of semiconducting material, the process is nothing but a doping here. Okay. So here doping material which are depending upon here trivalent impurities are also pentavalent impurities. If we add a trivalent impurity to the pure type of semiconducting material, this process is a doping here. Then the materials which is to be formed here, a p-type semiconductor material, are if we add a pentavalent impurity to the pure type of semiconductor material, it is to be created a n-type semiconductor. Let me say you here what is the structure of the, what are the example for the pure type of semiconductor material, silicon and germanium. This is the structure, and this is the crystal structure of the germanium. You can easily observe that valence electrons which are available for the silicon or germanium is 4 electrons. So thicker one, bigger size, which is the atom, surroundings the atom, 4 valence electrons are there, dotted lines. You can easily observe that. Okay, 4, only 4 are there. So these are the valence electrons. 1, 2, 3, 4, 4 electrons. G means germanium, like that. What is the bond between the, that is a covalent bond? What are the valence electrons? These are the valence electrons. Okay, you can easily imagine that here. The structure is also given out here. Yeah. Doping is also there. What is a p-type semiconductor material? Let me say you here, a p-type semiconductor material means a trivalent impurity. Tri means 3, only 3 electrons are there, outermost electrons. If this trivalent impurity which is added to the pure type of semiconductor material. What is the pure type of silicon or germanium? What are the valence electrons, outermost electrons? 4 electrons are there. So out of 4, 3 electrons which are to be forming a covalent bond. The trivalent impurity is IN means indium. Indium is which is a trivalent impurity which is added to the germanium, and these 3 valence electrons which are to be forming with the 3 valence electrons of the germanium, and only one empty is there. That empty which is called as a hole here. That means this is to be searching out. That means any atom is having such a excess of electrons, so that if it is to be donating, it is to be acted to make a covalent bond with them. That's why here the p-type semiconducting materials which are the acceptors. Okay, and also one thing that you have to remember here, the majority charge carriers which are available in the p-type semiconductor material is a positive holes, and the minority charge carriers which are available in this p-type semiconductor is negative electrons. Next, this is a structure. Next, n-type semiconductor. What is n-type semiconductor material? You can see that here. If you add a pentavalent, penta means 5. So if you add a pentavalent impurity to the pure type of semiconductor material, pure is 4 electrons. 4 out of 4 covalent bonds which are formed. Okay, bismuth Sb is there, pentavalent, and also germanium, and one excess electron is there. That electron is a free electron. That means here in n-type semiconductor material, if you add a pentavalent impurity to the pure type of semiconductor material, those materials are n-type semiconductor materials. So the majority charge carriers which are available in the n-type semiconductor materials is electrons, 3 electrons. Minority charge carriers are positive holes. So here there is an excess amount of electrons which are available in the case of n-type. So it is to be searching out that if any atom is having a deficiency of electrons, so that it is to be donating the free electron to that atom, so that it is to be forming a covalent bond. That's why here these n-type semiconductor materials, you can call it as a donors. Okay, next, what is a PN junction diode? Junction diode, that means here when a p-type semiconductor material which is added to the n-type semiconductor material, that means here when a p-type semiconductor material is which is fused with the n-type semiconductor material, Then p-type consists of majority positive holes, n-type consists of majority negative electrons. When both these are to be fused with each other by using a specialized technique here, okay, a junction is to be formed. That means a junction which is to be separating the two different regions. That's why here this diode, you can call it as a PN diode, a junction diode. Getting my point? Okay. So here, whenever if you fuse these two different regions with each other, so here the p-type consists of a positive holes, n-type consists of negative electrons. The positive holes come across the junction and enter into the n region, and the negative electrons come across the junction and enter into the p region without applying any external potential difference or else source to that. So that it is to be losing their charges and become an ion, and it is to be forming a layer. That layer you can call it as a space charged region or else a depletion region. So that there is no charge at all. So that means surrounding the junction a layer is to be present there. So that is a consists of ions by losing the charge of the different atoms here. Charge carriers are here present. So that if you want to reduce it, you have to apply such a potential difference across the junction. So depending upon the silicon or germanium, and germanium needed only 0.3 electron volts and silicon needed 0.66 or 0.65 electron volts is needed to reduce the junction power. Okay, this is the depletion region. So that whenever the depletion region is to be reduced by applying such a potential to that to the potential barrier. That barrier, this voltage you can call it as a barrier voltage. Okay, VB is there. So yeah, similarly, the charge carriers from the p region into the n region and n region into the p region, these electrons and holes which is to be carried out by the charge, then you have to say that this diode is to be conduct the current here. Okay, this process you can call it as a biasing. What is forward bias and reverse bias? When the positive terminal of the battery which is connected to the p region and the negative terminal of the battery which is connected to the n region, you have to call it as a forward bias. So what it means here, p region consists of a positive holes, n region consists of a negative electron. Positive and n negative and negative. There is a here repulsive force should takes place here. Repulsive force between those charge carriers. That's why here you have to say that the charge carriers which are to be moving freely from the one region to the other. So in this case, the current conduction is to be takes place. You have to measure the current which is in milliamp. What about the reverse bias condition? The reverse bias condition means here when the positive terminal of the battery which is connected to the negative terminal of the n region, and the negative terminal of the battery which is connected to the p region. That means here p region consists of a positive holes and n region consists of a negative electrons. So these are attracting, not a repulsion. Repulsion should take place in the case of what do you say, in forward bias. In reverse bias, there is no here current conduction is to be takes place in the case of reverse bias. Why? Because of all these charge carriers which are attracted towards the here battery. That means here those are going to be losing their charges and become an ions. Ions are to be forming a layer. That layer is a depletion layer, so that the width of the depletion layer is to be increases in the case of reverse bias. That's why here the charge carriers cannot move freely by applying such a volt to the potential barrier, potential to the voltage potential barrier, so that these cannot move freely from the one region into the another region. So that's why here width is increases. So the current conduction is not to be takes place in case of reverse bias. Getting my point? Okay. So like that you have to read out and you have to draw the figure also. See here in reverse bias, whereas by applying and increasing such a voltage to the potential barrier, so there only at somewhat the you can see here for a germanium 0.3 is needed, for a silicon is 0.6. Okay, the diode symbol is like that, anode and cathode. So such a voltage, it is to be applied. So in the case of a reverse bias, BR means reverse bias. So that here at what voltage the flow of current is exponentially at simultaneously at avalanchely, uh, the current is to be coming out across the junction, so that voltage you can call it as a breakdown voltage. This breakdown voltage is you can call it as a Zener voltage. Okay, you have to remember. And also, what is Zener diode? Zener diode is the best example for the PN junction diode. This diode is heavily doped, and also which is worked in the case of a reverse bias. Okay, and you can observe in reverse bias a breakdown voltage, and also here avalanche breakdown voltage. That should be observed in the case of a Zener diode. You have to calculate and you have to explain in terms of this. Next, transistor configuration. What is the transistor configuration? What is the transistor? Trans plus resistor, transmitting the data by using the resistors. Okay. So what is the configuration of the transistor here? So transmitting the data means transmitting the signal by using the resistor. So in olden days we used to say that our forefathers, we are to be using a transistor. That means nothing but here a radio, a small type of radio. So here from Hyderabad, you are to be sending the signal at Adilabad or Nalgonda, whatever it may be. That person is to be utilizing that component and that instrument, and he is going to be here from Hyderabad sending the signal. There only is going to be receiving the signal. That where the signal is to be received by the instrument, that is nothing but here a transistor. That's why you can easily ask your forefathers, sir, grandpa, what is a transistor? He easily used it to say that yes, the transistor is nothing but a radio, like that. Okay, so here, uh, here that the transistors are so two types here, PNP transistor and NPN transistor. You can easily observe that means here what is a PNP and what is NPN. That means PNP. That means two diodes which are to be included in the case of a transistor here. That means um, when N-type material which is sandwiched between the two other P-types, or else when a P-type material which is sandwiched between the two other N-type, sandwiched. Why you to be says that here? Suppose if you see the sandwich, if you observe the sandwich, if you eat the sandwich here, top and bottom there is a bread slice is there. Between there is a tomato, cheese, cabbage, and something which is to be putting between the two bread slices. That means the top and bottom is same, and middle is portion is different. So like that here, PNP. What is a PNP transistor? P type is positive holes, N type is negative electrons. That means two when the N type semiconducting material is sandwiched between the two other P type, that is PNP. Or when P type material is sandwiched between the two other N type, NPN transistor. Okay. So the transistor consists of three terminals: emitter, base, collector. Emitter, base, collector here. So whenever you are to be using and functioning this transistor in biasing condition, uh, each and everywhere at input it is needed two components, and output is the two terminals. Sorry, one input is a two terminals, output is the two terminals. Total is four terminals. But a transistor consists of only three terminals. What is that? Left hand side is emitter, right hand side collector, middle portion is base. EBC. Okay, so that out of these three, one is to be commoning the for input as well as the output. That configuration is nothing but a common configuration. Suppose if base is common for input and output, common base. Emitter is common for input and output, common emitter. Collector is common for input and output, common collector. So like that here, one thing is that here the emitter base, that means what is the role of the emitter here, means the emitter which is to be sending the majority charge carriers towards the base. Okay, and base consists of minority charge carriers. Few of the minority charge carriers which are combined with the majority charge carriers remaining, which is sent towards the collector or which is injected towards the collector region. Okay, so that collector region which is to be collecting the charge carriers which are coming out from the base region. So that in this PNP or NPN transistor, which consists of two diodes or two junctions, what are those? Emitter base junction and emitter collector base junction. So that emitter base junction you can call it as a emitter diode, collector base junction you can call it as a collector diode. Emitter base region which is always in forward bias, collector base region which is always in reverse bias. Okay, you have to follow these rules to write it down and to work down it. Everything which is to be utilized. So here the transistor portion you can call it as emitter. Emitter current is IE. PNP means the arrow mark is to be giving out from the emitter towards the base. That is PNP. Or else if the arrow mark current is to be flowing from the collector to the base, that is NPN transistor. What is IE? Emitter current. RF is forward resistance, and RL is the load resistance, IC is the collector current, VC is the voltage, and so you see here PNP which is always in forward bias. PNP means P means positive holes which is connected to the positive terminal of the battery. You need not to observe here a signal here, a sine wave, that is a AC. In the case of AC, you have to observe the here fluctuations. Whereas if you use the battery here, no need to apply the here fluctuations. Only battery is there. Okay, Nandi? You can go for it. So like that, bipolar junction transistor. Okay, bipolar means in two way the current is to be flowing. Here, what are the input characteristics? What are the output characteristics? You can easily observe by doing the experiment also. Next, hybrid parameters. These are to be calling as a H parameters here. Okay, so what is the here output admittance and reverse voltage, forward current, input impedance, like that. Here it is to be denoting here different terminals. Here delta VIC by delta VCE and delta IC by delta VCE, like that. Here H alpha, HRE, HFE, HI, not H alpha, HIE, that is. Next, under common base configuration, base is common for input and output here, whereas to be using here voltmeters, ammeters, as well as the resistors. Okay, two types of different. What are the characteristics? You can go for it. Next, BJT, bipolar junction. In two way the current is to be flowing. BJT here. What is J1? Collector emitter diode. J2 is a collector diode. EBC is there, emitter base collector. PNP and NPN transistor is to be given out here. How the PNP as well as the NPN process is to be taken, just now we discussed that. You can go for it. But one thing that you have to draw the diagram for also. Hybrid equivalence here. This is the hybrid parameter. Hybrid input, it is needed to be two terminals. Output, it is needed to be other two plus 2 4 terminal network is there. Okay, transistor as a 2-port network, and here how it is to be here simplifying this, you can easily go for it. Yeah, see here V1 and I2. What are the 2-port network? How to be writing here in a matrix form here? V1 I2, H11, H12, H21, H22, and V2 I1. Not is a V1 I2. Okay, why? Because of you can easily observe in the case of equation. I1 is there, V2 is there, but here what is written here? V1 I2. That is print mistake. And also last one is H22, not only H2. You can see here H22. Okay, correct the equations. special semiconductor devices, field effective transistor, FET, okay, which consists of a source, grid, and drain, SGD. And if you use a P channel, or if you use a N channel here, how the current conduction is to be takes place here. See here, D means drain and G means grid, S is a source here. P channel, N channel, and grid means a gate here. D is a drain, S is a source here. Okay, how the internal voltage which is to be dropping out according to the whether it is a P channel or N channel, P type or N type channel, and also which is to be resulting here, how the depletion regions which is to be changing out. You can easily observe that case. And what are the transistor characteristics? What is a tunnel diode? Tunnel diode. Okay, according to the PN junction diode, how it is to be here utilizing, and how the here current conduction which is to be takes place by adding the different types of impurities. Okay, that is to be taken out. Next, under reverse bias, how it is to be worked out, under forward bias, how it is to be worked out. Unijunction UJT. UJ means UJT, which is only one direction and the current flow which is to be takes place. BJT is in two ways, whether it is in forward or whether it is in a reverse. Okay, that is UJT, BJT. Difference. Silicon control rectifier, SCR symbol is also given out here. SCR symbol. Okay, A means anode, C means cathode here, G means gate, AGC. Okay, whether it is a PNP or NPN, three diodes are there, J1 and J2. You can go for it. These are the best example for that. And transistor is an amplifier. How it is to be worked out? Yeah. PNP and NPN transistor. NPN, negative terminal of the battery which is connected to the N type. N type which is consists of a negative electron. There is a repulsive force. That means this is in forward bias. That means we are to be fulfilling the conditions. And right hand side is N type. N type consists of negative electrons, but positive, negative electrons which are attracting toward the positive terminal of the battery, you have to say that this is in reverse bias. Whenever the charge carriers which are attracting toward the terminal of the battery, that is reverse bias. Repulsion takes place forward, attraction takes place reverse bias. Thermal runway. Thermal runway. How the charge carriers which are to be moving out from the one region into the another region. So due to the minority charge carriers as well as the majority charge carriers, if it is to be taken out by the current here, how the current conduction is to be takes place, and how the temperature is to be increases with respect to these charge carriers mobile. Okay, that is related to the thermal runway. This is a very important short question. This is to be given. And a fixed bias arrangement is also self bias, fixed bias. Okay, now you can go for it. And also how the BJT is an amplifier. And by coming class, we will discuss about the introduction to the amplifiers. What is a feedback amplifier? How the feedback amplifier, positive feedback and negative feedback amplifiers are there. What is the Barkasian criteria? What is feedback? And what is an amplifier? How the strength of the signal which is to be enhanced by. That is the amplifier here. How the transistor is to be utilized and working as a amplifier here. That is to be discussed in the coming class. We are to be concluding by coming class here. Okay, Randy? Right. Thank you. Thank you. All the best.